on a Thursday. So this talk, as Brian said, is going to be about replication and evidence factors in observational studies. So using this talk, I'll be introducing to you the evidence factor analysis method in observational studies. You'll see that how using this method we can get more confident causal evidence if there is a causal effect using observational studies. So the plan is to do 4 things. Number 1, I'll give you the background or sort of the motivation behind why we want to use this method. Number 2, I'll show you the 4 main steps or sort of main ingredients that goes into it. Number 3, I'll actually show you using a complete study of the effectiveness of Catholic schooling packages or sort of the course you might want to use for this method. So if you have any questions in between, feel free to interrupt me. I'm happy to answer any short questions while I'm doing my presentation. Okay, so before I really get into the topic of evidence factor, let me start with a short story from history. So this story is about the elementary charge. So it's the charge of a single electron. The number in red that you see on your screen is the exact number, the number that we know to be exact of the charge of a single electron. And this was established to be exact in 2019, and there is nothing that we know for sure or that is we know in the whole world that is more exact than this number. But obviously the discovery of this number that goes back decades. So the Robert Millikan, who was from Chicago, he was awarded the Nobel Prize in Physics in 1923, and the citation read for his work on the elementary charge of electricity. The paper was published in 1913 by Millikan, where he used a newly developed technology, which is known nowadays as oil drop experiment, and he calculated the value of E, that's the charge of a single electron, up to a precision which is 6 times better than anything known before. And this was quite a sophisticated experiment, and even in today's standard, this is pretty sophisticated. So let's follow this story, the development, the calculation of E for like 2 decades starting 1913. So the timeline goes 1913, Millikan reports a number. I have zoomed in a lot, and on this scale, this number is in cross and the standard error are these 2 vertical lines. And using the oil drop experiment, multiple articles, multiple research groups corroborated the same number, which eventually led to Millikan winning the Nobel Prize in 1923. In 1924, the Nobel Prize in Physics was awarded to Mane Seinban, and Seinban was working on a slightly different field. He was working on X-ray spectroscopy, and that's also a pretty sophisticated technology compared to that standard. And turned out that Seinban's PhD student, figured out a way that spectroscopy technology can be used to get a better estimate of Avogadro number, right? And he said that, okay, using Avogadro number, I can get a defined identification of E, and he calculated a defined number. The number, which was reported in 1928, was more than 3 standard error higher than what Millikan reported, right? So the number here is shown in the red. Arthur Eddington, who is more popularly known in our culture as the first person to find an evidence for in support of general theory of relativity using the solar eclipse experiment. And if you're a statistician, we might also know him as the person who had a little feud with Fisher, because Eddington was in support for least absolute deviation, Fisher was strong in support for least squares. But either way, in 1928, he used general theory of relativity and Pauli exclusion principle to calculate a defined value of E. So Eddington did not do any experiment, unlike the other two studies, other two methods, his calculation was completely based on theory. And he said that the E should be much higher than Millikan's value. He writes, the discrepancy is about 3 times the probable standard error attributed to Millikan's value, and I cannot persuade myself that the fault lies with the theory. Even though both those studies were reported, the second and the third one were reported in 1928, they were not communicated with each other. So as a part of sort of addition to his paper, Eddington writes, I have learned of a new determination of E by Sine-Ban, which is higher. I understand a higher value is obtained, which would closely confirm the present theory. So sort of what do we see? We see that of these three, the second and third sort of matches with each other, and they are different from all the ones and a numerous ones that were obtained by the oil drop experiment, right? But all these three methods somehow use very different tools to get the same number, the same quantity E. So to sort of summarize the whole development of this time, about 90 years from then, Professor David Bailey writes, a series of beautifully consistent results had shared a common bias. So this is about the first decade following Millikan's result, that became, the bias only became apparent when experiments were done by defined groups using different methods. So that was the crust of the story. Now we know that the true value that we know to be exact is actually much further than all the numbers they had. And we know a few things. We know that Millikan's calculation was biased because he used an incorrect calibration of viscosity in his calculation. And we also know the number that was reported earlier in the slide is exact by using at least 4 different methods. So my moral of the story is biases can replicate. So if there is a bias and there is possibility of bias in any experiment, if you repeat the experiment, the bias is going to replicate and you cannot get rid of it by repeating the experiment. So replication is an attempt to resolve the principal sources of uncertainty that linger from previous studies. There is little to no point in repeating a study if doing so reproduces the same uncertainty. So to be fruitful, to be useful, a replication should eliminate or reduce or at least vary the principal source of uncertainty. Now this observation obviously is not completely new. Previously, for example, epidemiologist Marvin Susser had wrote, the epidemiologist seeks consistency of results in a variety of repeated tests, or the strength of the argument rests on the fact that diverse approaches produces similar results. Much before Susser, Charles Peirce, for example, wrote, we should trust rather to the multitude and variety of arguments than to the conclusiveness of any one. Our reasoning should not form a chain which is no stronger than its weakest link, but a cable whose fibers may be even so slender, provided they are sufficiently numerous and intimately connected. So based on these arguments that we have got now, how do I apply them to observational studies and our causal inference questions? So let's go to observational study. In an observational study, the principal source of uncertainty stems from the absence of random assignment. That means that it's inevitable that the adjustment for the observed covariates, the measured covariates, may have failed to render comparable treatment groups being compared. If that happens, then in replicating an observational study, we need to remove or disrupt or at least vary this bias. And that would help us to determine whether the ostensible effects of the treatment reappear or vanish. So the plan of this talk, the rest of the talk, is to propose a principal method by which in an observational study, in a single observational study, we can provide varied and essentially independent evidence, evidence that becomes more difficult to attribute to bias because of its variety. And we also want to measure and quantify the resulting strengthening of the evidence for the effect and against the bias. Okay, so sort of the anchor slide for the rest of this talk is going to be this slide. I'll come back to it a few times. This lists the 4 different pieces of an evidence factor analysis. What goes into it? Number 1, we want in a single study comparisons that depend on substantially different assumptions. Number 2, the comparisons should be statistically independent. Number 3, even when other comparisons are biased, the current test is still valid. We want to integrate the evidence from the evidence factors. So I have clubbed sort of number 2 and 3 together because those are more technical points, and I want to show you at least some calculations how to get to those points. So let's look at number 2 and 3. Is it possible in a single observational study comparisons which are statistically independent? And is it possible that even when one comparison is biased, the other comparison is still fine, still statistically independent and still valid? So let me show using a toy example that it is indeed possible, and then I'll tell you how this example can be generalized to a large extent. In this toy example, I'm considering you have 3 subjects numbered A, B, and C, and you have 3 treatment positions, 1, 2, and 3. So we have the hypothesis that the treatment positions do not change the outcome. That means the potential outcomes under any of the 3 treatment positions are the same for every subject. That's the null hypothesis. So consider 2 comparisons, which I am denoting by R1 parenthesis 3 and R2 parenthesis 2. The first one is the rank of the subject in position 1, in treatment position 1, among all the 3 subjects. So if the outcomes don't have any ties, R13 is going to be either 1 or 2 or 3. R23, on the other hand, is the rank of the subject in position 2 of the subjects in position 2 and 3. Okay? So even without ties, it's going to be either 1 or 2. Okay. So I haven't talked about the treatment assignment yet. I just have sent you an idea of the hypothesis and the 2 comparisons. So let's consider one treatment assignment method, which is completely random assignment. So if the 3 subjects were assigned randomly to the 3 treatment positions, then just using a few arguments, we can show that R13 and R22 are statistically independent.
Sorry, can I ask you a quick question?
Sure.
Does treatment position mean something different than just treatment? Like, what is it because they're in a special order? Is that what the position means?
I mean, you could think of it as a special order, or you could think of it just first one is treatment, the other 2 are control. So it doesn't have to be unique positions. It's just a position that the designer has fixed a priori.
Okay, thanks.
Yeah. Okay, so these 2, R13 and R22, can easily be shown to be statistically independent, and this follows from because what happens is, because the treatment assignment is random and because the null hypothesis is just nothing happens if you get a defined treatment, or if you are positioned into a defined treatment position, your outcome remains the same, which means that all possible values of R13 and R22 are equally likely. So all of them are 1 over 3 factorial, which means marginally R22 has a marginal distribution, which is just a coin flip. And the conditional distribution of R13 given R22 is again uniform. So you can see using just the fact that the treatment assignment was random, R13 and R22 are independent. It's a very simple calculation, follows immediately once you write down the joint. Now suppose the subjects were not assigned randomly. If an assignment was biased, what happens? So suppose treatment position was filled first. So the designer first picked one of the three subjects randomly, put that subject into position 1, and it was twice more likely of the remaining two subjects, the subject with higher outcome will take position 2. So there we did not have randomization. Obviously, that if that happens, then even when the null hypothesis is true, all values of R13 and R22 are not equally likely. R22 will tend to be higher, tend to be larger, tend to be 1 more than 2. But yet we can show the following things. There is no problem with R13. So distribution of R13 is still uniform. So it's still 1/3 for all possible values. So first comparison is still valid. And you can also show that even when R23, sorry, this should have been R22, even when the second one is not valid, they are still independent. So the bias that is lingering in the second one is not affecting the comparison in the first one. So the result that I showed you briefly in the previous slides can be generalized to a large extent. First,
sorry to interrupt. Were those? This is great. Thank you. Are the last couple lines that you said, is that all? That's all under the null hypothesis. Is that correct?
Right. It's correct. So
okay.
This is under the null. Yeah.
Great. Thank you.
Yeah. Right. So the generalization goes in various directions. Number one, we do not need to rely on sequential assignment. So it can be shown that there is a little bit of algebra behind it, where if the first test is invariant under the right kind of permutation, the independence still works, or the previous set of results still work. The second generalization, I used ranks before. You don't need to use ranks. You can use almost any test you want. You lose something. What you lose is you don't get exact independence. You get something called a near independence. And near independence is going to be sufficient for us. I'll precisely define what near independence is later on in this talk. Another one, I showed you that one-way bias cannot affect the other one, but you can bias both of them and you can still get near independence. Then you don't need to do 2 of them. You can do multiple ones, and we'll actually be doing 3 evidence factors in our example, in our empirical study. And finally, you don't need to use every time just a part of the data. You can use the whole data all the time. Obviously, you need a little bit of more assumption in it. So all of these generalizations are important, or provide a flexibility to use evidence factors analysis method in a variety of situations. So coming back to the anchor slide, I showed you, or I actually explained a little bit of the idea behind 2 and 3. Now I want to show you how to get to the first point. The first point is we want comparisons that depend on substantially defined assumptions. So to do this, I'll now introduce my empirical study. We are interested in the effect of Catholic high school versus public high schools on earning in their mid-career of graduates. So if there is an effect of Catholic high school on income, then there are a few testable implications. Among comparable students, Number one, we should see Catholic school students will earn more than public school students. Number two, because being raised Catholic encourages going to Catholic school, if you consider raised Catholic as an IV, students who are raised Catholic will earn more than students who are not raised Catholic. Number three, if you're from a region which has a Catholic school, so if you have geographic accessibility of Catholic school, that also encourages the individual to go to Catholic school. So that works as an instrument, which implies that growing up in areas where Catholic schools are more accessible will earn more. So the first one is just a direct comparison that we are all familiar with, comparison between so each of these comparisons has been published in papers, but not typically in the same paper. What we want to do is, using the same data, we'll use evidence factors analysis, where we'll do each of these three comparisons, and they'll be independent of one another. Okay, so the plan is now that I'll go through these three comparisons one by one, sort of the idea behind the comparison or the assumption that goes behind it. And then I'll come back and show you what the data looks like and what our analysis looks like. The first comparison is a direct comparison, and you can easily see or you can easily argue that young adults who go to Catholic school typically have parents with more ambition about their children or greater concern with education. So if that happens, you won't be able to measure ambition or discipline or things like that accurately. Thus, observing higher incomes among those with a Catholic school education leaves us in doubt about the effect caused by education, because of those confounders that might not be measured. But just because it may be biased, it does not mean we just dismiss this comparison. A direct comparison may actually be insensitive to larger biases, at least in comparison to comparisons using instrumental variables where the instrument is particularly weak. And we show this, that the direct comparison can be insensitive to larger biases using calculations of design sensitivity in the paper. The paper I mentioned here, I'll cite at the very end. The second comparison, that's the instrumental variable comparison using raised Catholic. And this is our typical picture for an instrumental variable analysis. We have to assume that there is an exclusion restriction, that raised Catholic can only change earning through its effect on attending Catholic school. It cannot be associated with unmeasured confounders, and it has to be associated with Catholic schooling. And the third one, the third comparison, is using the geographic accessibility of Catholic school as an instrument. So again, it relies on a defined set of assumptions, another exclusion restriction, association with Catholic schooling, and ignorability with respect to unmeasured confounders. Okay. So these are our three comparisons, and let's look at the study structure. In this study, we are using Wisconsin longitudinal study, where we have data on about 4,400 or slightly above 44. And our outcome is going to be their earning at age 35. So in this table, I'm sort of showing you the structure of our analysis. So the three comparisons are going to be three stratified comparisons. In the first comparison, we'll compare urban and rural, which is the comparison between the geographic accessibility. In the second comparison, we'll have comparison between raised Catholic against not being raised Catholic. stratified by urban and rural, and the third comparison is going to stratify both on region, also on religion, and compare Catholic school versus public school. You can see that in urban areas, the proportion of people going to Catholic school is much higher than in rural areas. In urban regions, if you are raised Catholic, the chance of going to Catholic school is much higher compared to in rural areas, and it's almost zero in urban areas, at least at that point of time in urban areas if you are not raised Catholic. So we can see at least there is a push, there is a strong push by each of those two instruments for going to Catholic school. As I said, the direct comparison is going to focus on comparing between Catholic school students and public school students, which we stratify on the other ones. The comparison using raised Catholic as an IV will stratify on urban and rural, and the comparison for geographic accessibility will compare similar people in urban and rural areas without any further stratification using the other ones. So I'll report a result in a few slides that these three comparisons, the way they are structured here, these three stratified comparisons are nearly independent. So just briefly, in our method, we adjust for IQ score, parents' education, parents' income, parents' occupational practice as measured covariates. So in our analysis, we also wanted to do sensitivity analysis. So we allowed for some amount of unmeasured confounding to be present. So just a short introduction of sensitivity analysis in this context. A sensitivity analysis in one way or another relaxes a doubtful assumption. It does not replace this condition by an incompatible condition or incompatible assumption. So we gradually relax the assumption of no unmeasured confounding. To do that, we're going to use an index. The index is going to be Rosenbaum's gamma. It's by Paul Rosenbaum. What the gamma says, gamma is a parameterization of the maximum odds ratio that one gets of between comparable people, the maximum odds ratio that one of them gets treated and the other one is not treated because of unmeasured confounders. So you can sort of understand it by saying that if gamma equal to 1, then they have equal odds of getting treated or controlled. So gamma equal to 1 means there is no unmeasured confounders. If gamma equal to 2, then because of unmeasured confounders, one of them can have twice the chance of getting treated compared to the other one. So higher amount of gamma means higher amount of possible unmeasured confounding. So in a sensitivity analysis, what we can do is, given a comparison and given a value of gamma, we can find the maximum possible value of the p-value. In other words, given a comparison and given a gamma, we can calculate the evidence that still remains if we allow that kind of relaxation of our unmeasured confounding assumption. And if this upper bound, this p-value upper bound is still small, then we know that a bias of gamma is not sufficient to refute our evidence. And because we have three comparisons, we have three sets of p-values using three sets of gammas. So the theoretical result says the following. It says that if Catholic schooling had no effect, so again, if the null hypothesis was true, if the instruments satisfied exclusion restrictions, and if the unmeasured bias from unmeasured confounding were at most gamma 1, gamma 2, and gamma 3, then the three p-values or the three p-value upper bounds are nearly independent, by which I mean the following. this joint distribution of the three, P1, P2, and P3 is stochastically larger than the uniform distribution on a cube, unit cube. And that's the mathematical statement of it. For any function f that is increasing, the probability that f has a higher value is higher than f has a higher value under a uniform distribution. So this is the formulation, or this is the definition of near independence that we rely on for our later discussion. So using this,
sorry to interrupt. I just wanted to ask about the definition of near independence. Can you say a little bit more about how it relates to independence?
Right. So this would be exactly independent if I have equality here. Right? Because if I have this probability as same equal to this probability, then it's fine. But we don't have equality, we have greater than or equality. That means the joint distribution can only give you higher values than an uniform. And the higher value for us means the evidence against the alternative, right? So we are okay as long as under the null, the evidence against the alternative is higher than what would have been if everything was independent.
I see. Yeah, I'm still wrapping my head around it. Is it in a way kind of equal or better in terms of the p-value distribution that compared to independent?
Right. So
it's very vague what I'm saying, but yeah.
Yeah, I completely agree. So if you just keep the three things and if you have just one of them, right? So usually we define p-value as probability p less than equal to alpha is less than equal to alpha, right? Rather than equal to alpha. So this is exactly the same sort of inequality. It's saying that, okay, we are okay with a higher than alpha rather than a alpha. Yeah.
I see. Great. Yeah. Thank you.
Okay. So using the three methods, we calculated the numbers. So in this table, I'm showing you a bunch of numbers, but let's just focus on a few of them. So the one in the red, or the red brackets over here, highlights gamma equal to 1, which means we are not assuming any unmeasured confounding, and we got 3 p-values, which are all highly significant. If you increase and if you allow some amount of bias, then you get a slightly higher number of p-value, and except for the third comparison, the other two comparisons are no longer significant at level alpha. But at least we have to be more careful here. We are looking at a bunch of p-values together, and as a statistician, we know that you can't do that. You can't look at just a bunch of p-values and compare each of them to level alpha. We'll do something more smarter in a moment. But I'll mention that gamma can be interpreted also as 2 parameters. So for example, gamma equal to 1.25 is equivalent to an unmeasured confounder that for 2 otherwise similar units doubles the odds of being treated and also doubles the chance of a higher outcome. So that's how it connects to both treatment and outcome. Given a value of gamma, you can get these defined 2 numbers. Okay, so now that we have that bigger table, how do I integrate all those numbers for our integrated evidence factor analysis? So the idea behind doing all of this is to use the near independence. So here is where the near independence is really crucial here, and you can, if you just assume independence, you can combine them using meta-analytic tool, right? So if you have independent p-values, Fisher's p-value method or some other p-value method will be able to combine them. The definition of near independence is such that if you use Fisher's p-value method or any of the standard p-value methods, it will still give you a valid combined p-value. And that's why that inequality goes in that direction. So in our analysis, we used a slightly generalized version of Fisher's p-value method, which is called the truncated product method, which focuses most on the smaller p-values. So it multiplies, rather than multiplying all the p-values, which Fisher's method do, it multiplies the p-values which are smaller than a cutoff. And it has a null distribution, which is a mixture of, which is a binomial mixture of gammas. It's a nice paper by Zekin et al. In 2002, who proves this null distribution. So what I have done now in this table is I am highlighting the combined p-value, which combines the three numbers along the rows. So this 0 is combining these three numbers, and we can do that because our theorem says they are nearly independent, and so on. Now, if we are happy with the value of gamma, then gamma equal to 1.2 still gives us a combined evidence which is strong enough at level alpha. We can do more, and we would like to do more. We would like to say, can, or at least out of these three comparison, is one of these really too influential that we want to be? If one of them is too influential and the other ones are just not informative, then we cannot rely on that evidence. So most precisely, I want to ask the following question. How much evidence for the effect of Catholic schooling is provided by at least two of the three comparisons? If it's provided by just one of them, we are not okay. We need at least two of them. And you can answer this by calculating what is called a partial conjunction of p-values, which here turns out to be just combining the largest of the two p-values. And it turns out, at least in this table, in each row, the largest two p-values are always the first and the second one. This is always the smallest. So the comparison using urban and rural always gives me a much smaller p-value than the other ones. And if I do at least two factors support calculation, it will combine the first comparison and the second comparison, the p-values are the following. Now we see the evidence at gamma equal to 1.2 is no longer that significant, and it's actually not significant, much higher, 0.34. Again, we need to be cautious. We're again looking at two columns together, and you need relationship it controls the family wise error rate. Okay. So Brian, how much time do I have?
You've got, I'll just chime in there, B. Brian. You have about, so the whole thing goes to about 1:15, so maybe finish up in the next 5 to 10 minutes.
Okay, sounds great. Okay. So I'll briefly say what the conclusion of this analysis was. Using this table, we know that if there is no hidden bias, that is when gamma equal to 1, then there is evidence, or we find evidence of Catholic schooling effect from using each of the three independent comparisons. At gamma equal to 1.1, there is evidence of two independent factors concurring in finding Catholic school effect. But when gamma equal to 1.2, the evidence mostly relies on the urban-rural comparison. So the inference of a Catholic school effect depends rather heavily on the validity of one of those three, that is the urban-rural as an IV. And you can go a little bit further to investigate whether you can rely on the urban-rural comparison. And it turns out, I'll not go into details on this, that you can indeed, you should indeed be cautious that urban-rural is not going to be a valid IV because it will most likely violate the exclusion restriction. So let me discuss a little bit about the implementation. There are three things that goes into implementation of an evidence factor analysis. You need to be careful about the design and the analysis separately. The design is slightly different from what we are used to. It's no longer your typical pair mesh designs. So for example, the way we did it, we used stratification method and we used the package blocking challenge. But you can also use other designs. For example, you can use multiple treatment groups, matching on multiple treatment groups. And we have a nice set of results using more of an algorithmic perspective to this design problem. So either of these two packages can be helpful if you're looking for how to start with an evidence factor analysis. Number two and number three on the same slide. Number two is we are using p-value upper bounds, and as I mentioned, the book by Rosenbaum 2002, Observational Studies, is a helpful starting point of how to get those p-values. The numbers I showed you, I got it from the R package SameStrat, so that does sensitivity analysis under a stratified design. And number three, which was the later part of our discussion, how to integrate the numbers. And as I mentioned, you can use any those methods are always easy to implement or available in R or other packages. So those are the main tools that you need. Obviously, there is a planning phase, how to plan an evidence factor analysis, and that often changes by problem to problem. So in conclusion, in observational studies, both biases and treatment effects can replicate across independent studies. So replication is not repetition. If replication amounts to disturbing the principal potential bias, then a single observational study can replicate itself by performing several independent comparisons that are affected by defined biases. So that's the goal behind our evidence factor analysis. And if you are able to perform an evidence factor analysis, what can you learn from it? One, the integrated evidence from the evidence factors can strengthen the causal conclusion. But if they don't agree with each other, if the evidence factors give us evidence that are in different directions, then we'll suggest caution. So both these are possible. Final two bullet points. A design that always encourages causal conclusion, a design that cannot suggest caution or restraint, is not a good design. An easy way to publish a false causal conclusion would be to decline to look for evidence that might reveal bias if present. So finally, these are my references. The talk was mostly, or the application was mostly based on this paper by me, Dylan Small, and Paul Rosenbaum from UPenn at JASA. You can find some theory behind the evidence factor analysis in the other papers. And thank you everyone again for listening, and I'm happy to take any questions if you have.
All right, I'm pretty sure I'm unmuted now, so thank you very much, Bikram. Does anyone have any questions to start?
I'll just interject there. I'd like to just thank the speaker. Let's just give a round of applause. I'll give you I'm representing everyone here with a round of applause. But then I'll pass back to as Brian said, open it up for questions. That was a great talk. Thank you so much. You don't need to raise your hand if you want to ask.
Okay.
Just unmute yourself and dive in.
Hi, I'd like to ask a question. First, thank you very much for the very interesting talks. And I knew about some of the evidence factors before from Paul Rosenbaum's book, and I find them very, very interesting. But I think I have a couple of questions, but I only want to start with one and such that others can ask questions too. My main problem is when I, let's say, use different instruments here and when I use different control groups, each analysis I conduct looks essentially at a different comply average treatment effects where the meaning is quite different. So if we assume that there's quite a bit of effect heterogeneity across those, let's say, control groups and across the instruments used, right? So what can we actually learn from it if we don't know how much effect heterogeneity is in there?
Right. So I completely agree with you. So I find it sometimes difficult when using evidence factor, particularly using instrument, because as you said, they're looking at defined subgroups. They're looking at defined, yeah. So the way I think about it, and the way I think is cleanest for me to think about is it's an evidence against the null, the sharp null, I guess. So if you're not happy with just testing the sharp null, you have to go beyond evidence factors and somehow use something else. So I have been trying in recent work to go beyond evidence factors, and I think the best way to do that is not using a single study, but using multiple studies which can do more things than just doing one of them. So that's how I think about it. But I completely agree with your criticism of the current approach that exists.
Great. So let's pass it to. Oh, go ahead.
I have a question that I think is kind of similar to what Michael was asking about before, which is, so talking about like near independence, is there a sort, like before you do the math to try to figure out whether the quantities are near independent, is there a sort of qualitative or intuitive way to think about whether two things might be near independent, or like what you would expect to be near independent?
Oh, sure. So, I mean, we sort of have an idea by now that whether it's going to be near independent or not, but at least in a couple of situations before doing the math, what we did is we just ran a simulation and we plotted the p-values against one another. So if they are nearly independent under the null, you'll see that if there are two p-values, it's going to be just uniformly scattered on the xy plane from 0 to 1, 0 to 1. So that's an easy way to get an empirical or an understanding of whether they're going to be near independent. But sort of by now we know there are at least a few structure, and that goes through, sorry, essentially that goes through the first generalization, the first path to generalization that I mentioned, yeah, over here. So given a couple of analyses, if you can check that these sort of assumptions are hold, and they are typically not very difficult to check, then you know it's going to be nearly independent.
Okay, that makes sense.
Yeah.
Anyone else have questions?
I can ask another one, kind of related to the previous one. So I also have problems is when we combine it with sensitivity analysis and here the gammas. It's the same as before when we use different control groups and make some, let's say, statistical adjustments or different instruments, right? So there is no guarantee that these methods actually remove the same amount of bias in each of the analyses. It could happen that in some studies the bias tremendously increases due to the adjustment, because the data generating processes in different subpopulations or by using different instruments here are quite different. Right, so I'm a little bit worried if we then use the same gamma for each study. I think we would need to use subject matter knowledge and carefully think about which gamma to use for each of those within study replications. Otherwise, I'm a little bit afraid that it's getting very easily everything misleading. The other thing is also the choice of the gammas, right? So when I just choose a specific gamma, then I might achieve the independence, right? But it might not be the appropriate choice with regard to the real presumed quantity of bias we might think might be a problem in this study.
Okay, so yeah, so let me take that couple of points one at a time. So the choice of gamma, as you said, should actually change from comparison to comparison. And in this calculation, I did not show it, but in other works, we have actually used different gammas for different comparisons. And that obviously makes sense. In one comparisons, we are sure that the gamma should be higher. We haven't faced a situation where we know that one gamma would be like some function of the other gamma. So if that happens, that gives us a defined kind of relationship. The other point is how do I choose the value of gamma? Well, I mean, we have sort of few benchmarks. We know that at least in Paul's book, he reports that in smoking and lung cancer study, the value of gamma was 5 point something. So if your analysis is insensitive up to 5 point something gamma, then you are at that regime. So you'll be happy. So if it is something like 1.25, which is where we are here, it doesn't seem like it's going to stand out as the smoking and lung cancer study standard out. So you need extra calculation, you need extra studies to figure out if you can get more reliable evidence for your analysis.
May I briefly reply to this? So in general, I agree. So if you have a gamma of 5, it makes you probably more likely happy, but it's no guarantee. Just assume a case where you do, let's say, some covariate adjustment or matching, and you match on an instrumental variable, right? Then you end up with a study with a huge bias, right? And then it might seem that it's seemingly robust to a gamma of 0.5, but only due to the with these things. We need to think about what did you do in the first step to make sense of the sensitivity analysis.
That's interesting. Yeah, that's very interesting. You are right. So if you are purposefully or if you are wrongfully just introducing a lot of bias, then anything that is truly insignificant is not going to be good.
Yes, that's unfortunately what people usually don't pay too much attention to it. The sensitivity analysis depends on what you did in your analysis. And you have to choose the gammas based on what you did so far. Right? Then you choose different gammas based on this one. Only one follow-up question. How about power issues when you look at these different instruments for different subpopulations? I would assume you get really power problems here. And then what are the implications for the analysis here?
I mean, in terms of power, we did not check power with different treatment effect sizes. Our point of investigation was when is it going to work compared to, let's say, your typical two-state least squares method. So, and we saw that, two-state least square method can fail very easily. So if anything goes wrong with it, with any of the instruments, if any unmeasured confounding is there, if any exclusion restriction violates, two-state least square method will easily fail compared to like our method, which will still give you the right power. That's what we looked at. Yeah.
Great. Any additional questions? I wanted to ask, and maybe as a last question, what's your if you want to say for a minute or two about your current research and some of the questions that you're working on. You don't have to. I don't mean to put you on the spot, but I'm just curious. What are some future directions that you're interested in?
Yeah, so I'm happy to talk about it. So currently, I am working on the idea behind my current research is to go beyond just an identification of an causal estimate using some method. What I want to do is I want to use different tools, different methods to combine them and somehow give us more robust and more reliable causal estimate. So so I did not mention it in this talk, but in sort of an epidemiology literature, there is something called triangulation, which has been formalized now. So triangulation kind of tries to get to the same point that you need different ways of looking at the causal estimate, and if they give you the same result, you'll be able to get a more reliable causal inference. So what I'm working on now is combining triangulation methods using, let's say, not only instruments, but also native controls, using sensitivity analysis. The different kind of tool that we have, can that be used in a formal way? It's not, we don't want to do ad hoc stuff. We want to use them in a formal method and give a more principled.
Thank you. That's very exciting. So I just want to thank Dr. Karmakar once again for excellent talk. I learned a lot, and yeah, thank you so much for coming and speaking here. I really appreciate it.
Thank you for having me. I really enjoyed
Applause
it.
here.
And everyone. Thank you.
Thank you.
Thanks.
Great. And then Brian, do you happen to know our next, I'm just looking at my calendar for the next calls of
I think
inference.
the next one is the one that's joint with this Bayesian spatial group with Georgia.
Yeah, that's right.
Georgia, which is,
I'll put it in the chat.
Is it Tuesday or Wednesday?
It's this upcoming Wednesday. So it's this is our next speaker. This is on upcoming Wednesday at noon. Well, and you'll see an announcement, but just mark your calendar. So fantastic. Great. And Brian, anything else?
All right. Thanks, everyone. We'll see you next time, and we look forward to hearing more from Dr. Karmakar in the future.
Thanks, everyone. Bye.
So long.
Great. Thank you so much. Take care, everyone.